Good evening and welcome to another video session from Training Made Clear on the Imperial and the Metric System. And today we're going to be looking at lesson number 5 about pressure. I've decided to make this video in 2 parts. The first part will deal mainly with the Imperial and the Metric System. And then the second part will just to give you more insight into pressure and things that you should know about pressure. So let's begin with part number 1. As you know, in the Imperial and the Metric System, we have these 2 systems which affect us whenever we do anything like length and distance, mass and weight, volume, temperature, pressure, flow, even currency. These 2 systems seem to run through all of these different subjects. So this whole series on the Imperial and Metric System will consist of basically 8 lessons, but lesson 5 will be in 2 parts. So ask yourself, what is pressure? Pressure is the force applied perpendicular to the surface of an object per unit area over which that force is distributed. Pressure increases with depth. If you look at this drawing on the left at the bottom, you can see that the higher the column of water goes, the further the water will shoot from the bottom spout. The middle spout will go maybe half that distance, and the top spout will be the shallowest, because the pressure at the top is less than the pressure at the bottom. The force is per unit area, and the formula is pressure is equal to force divided by area. If you take a look at the different pressure units, the primary pressure units for the 2 different systems, the metric system, the main unit is the Pascal, and it's measured in newtons per square meter. The Imperial is measured in pounds per square inch, which is called PSI. In the metric SI pressure units, we have a whole lot of different units that we use called Pascal, kilopascal, megapascal, bar, and atmosphere. The symbols are PA, KPA, MPA, bar, and ATM. And you can see basically what the values would be looking like at those different values. The Imperial pressure units, the unit is pounds per square inch, inches of mercury, pounds per square foot, or atmosphere. The symbols will be PSI, INHG, which is inches of mercury, PSF, and ATM for atmosphere. The metric system pressure units, the historical development. The Pascal, PA, the origin, where it came from, it was named after Blaise Pascal, 1623 to 1662. Pascal studied fluid pressure, hydrostatics, and atmospheric pressure. Defined as 1 Pascal is equal to 1 Newton per square meter. The bar, the origin, was from the Greek baros, which meant weight. It was introduced in the early 1900s and defined as 1 bar is equal to 100,000 Pascal. Why it exists? It is close to atmospheric pressure and more practical than large Pascal numbers. The atmospheric pressure, the origin came based on the average sea level air pressure, formalized in the 19th century and defined as 1 atmosphere is equal to 101,325 Pascal. So that's just over 1 bar. Millimeters Hg or torr. The origin, Evangelista Torricelli, 1643, invented the mercury barometer. Measured pressure by the height of the mercury column. It was defined as 1 torr is equal to 1 over 760 atmospheres, which is equal to 30 inches mercury, roughly. The usage was basically used in medicine to measure blood pressure and in vacuum systems. The Imperial English System pressure units, the historical development. Pounds per square inch. The origin comes from the British engineering practice that combines pounds force from Roman libra and inches from body-based measurements, defined as 1 psi, which equals to 1 foot-pound per square inch. The history of the inches of mercury. The origin, the same principle as millimeters Hg, but using inches. Developed for barometers in English-speaking countries. Usage was mainly aviation, in altimeters, and weather reports, US. Inches of water. The origin was used where pressures are very low. It's easier than mercury for HVAC measurements. Usage, ventilation systems, filters, and ductings. So inches of water is very small pressures, and normally it's used for measuring a differential across a filter to see whether it's blocked. Atmosphere, the imperial use, the same physical definition as metric, adopted for convenience rather than system purity. Why metric and imperial units developed differently? Look at the aspect. The basis for the metric was physics-based. For imperial, it was practical or mechanical. The aspect derived from was the force and the area. And for the imperial was also force and area. For the standardization, the international metric SI, and then you had the imperial, national, and industrial. The scale for metric is decimal, and the scale for imperial is fractional. The precision for metric is scientific, and for imperial it's engineering and trade. If you look at the right-hand side, this sketch that you see here is actually, you can say, a model of how a barometer works. Basically, you would fill that glass tube, which is sticking up in the air. You would fill it up to the very top, close the bottom with your finger, then submerge it into a basin which has got mercury in it, and then take your finger away and let the mercury drop. That amount that it drops is actually equal to the atmospheric pressure pressing on the mercury in the basin. The vacuum area that we see at the top is basically if you were able to pull all the air out of the atmosphere, that bar would have gone to the very top. And that would have equaled 30 inches of mercury. Conversion comparisons. Metric, if we say 1 Pascal, then it's equal to 0.000145 psi. Or 1 kilopascal is equal to 0.145 psi. Or 100 kilopascal equals 14.5 psi. The reason I've made that so dark is that this is a very good number to remember. When you want to do calculations, if you have this one in your head, you can calculate most of the others. Because you can see the 145 stays there. It's just the comma that will be moving. So if you know what kilopascals, pascals, megapascals actually means, then you know where to put your point. Also note the very last one. 1 atmosphere is 14.7 psi. Very close to the same 100 kPa, 14.5 psi. You can almost say that an atmosphere is 100 kPa, rounded off. And that would be 14.5 psi rounded off. Atmospheric pressure at sea level. For the metric system, that is 101.325 kPa. For the imperial system, it is 14,7 psi. For the barometric, it is 29,92, which is rounded off to 30 inches mercury. Key differences summarized. If you look at the base unit for metric, it's Pascal. For imperial, PSI. Area reference is square meter, where imperial is square inch. Used globally, for metric, yes, international standard. For imperial, mainly US and legacy systems. Scientific use for metric is standard. For imperial, it's very rare. Engineering clarity for metric SI, that is high decimal based. For imperial, clarity is less intuitive because it works with fractions. Why is metric preferred in engineering? Well, because it's decimal based, multiplied by 10. All the scales are in decimal. It's consistent. The units across force and area and energy. There's fewer conversion errors. Pressure scale diagram, ruler type. So we're looking at pressure and we're increasing this pressure from 0 kPa up to 100 megapascals. And at each of those different values, we are saying this is where you will normally see this. 0 kPa is a perfect vacuum in space. If we look at 101 kPa, we're looking at atmospheric pressure at sea level. For imperial, it will be 14,7. Low car tire pressure, normally around about 200 kPa, which is 29 psi. 300 kPa could be normal car tire pressure, 43 psi. When you start looking at trucks, you go up to 500 kPa. When you start looking at hydraulics, you go into 1 megapascal, which is 1,000 kPa, or 145 psi. Industrial systems, 10 megapascals, which is 1,450 psi, and so on. Visual comparison insights. The metric scale grows cleanly by multiples of 10, from kilopascals to megapascals. The imperial scale grows in larger uneven numbers, like 1 megapascal is equal to 145 psi. Just a simple memory trick for you to remember: force is how hard you push. Pressure is how spread out the push is. Stress is how the material feels the push inside. Force, the definition for force is a push or a pull acting on an object, and the formula for that is F is equal to m times a, which is mass times acceleration. For the metric system, it's measured in newtons, and for the imperial system, it is measured in pounds force. For pressure, the definition: pressure is a force applied uniformly over an area, usually by a fluid. And the formula is P is equal to F divided by A. The units for the system metric is pascals or Newton meters squared. And imperial is PSI in pound force per square inch. Liquid pressure basics, a static head. Liquid pressure depends on depth, not container shape. The formula for that is P is equal to rho GH, where rho is the liquid density, and for water that would be a SG of 1. The gravity is 9.81 meters per second squared, and the height is the liquid height that you would see in the head. Let's take a look at some water heads, pressure conversions. 1 meter of water would equal 0.098 bar. In kPa, it would be 9.8. In pressure, psi, it would be 1,42 psi. 5 meters of water would be 0.49 bar, which is 49 kPa, and that's the same as 7.1 psi in Imperial. 10 meters, and I've highlighted this one because this is a good one for you to remember so that you can work out many of the other values. 10 meters of water is 0.98 bar, rounded off to 1 bar, very close to 1 bar. In kPa, it would be 98 kPa, which is very close to 100 kPa. And in pressure, it would be 14.2, and most people think of it as 14.5 psi. And so we go on to all the other measurements that you see on this chart. The rule of thumb, 10 meters of water head equals 1 bar, which equals to 14.5 psi. As you can see, the green marks in the chart are written in green at the bottom, which is like the rule of thumb. Okay, we're going to look at the imperial liquid head in feet of water. Rule of thumb, 2.3 feet of water is equal to 1 psi. So if the head is 1 foot, then the pressure would be 4.33 psi. If it's 10 feet, then the pressure is 4.33 psi. And if it's 33.9 feet, it would be 14.7 psi. And that 14.7 psi is the same as 1 atmosphere. If we go over to the oil and heavier liquid examples, typical crude oil with a density of 0.850. Remember, water, the SG would have been 1, but for oil it will be 0.850 or 850 kilograms per cubic meter. So 10 meters of crude oil would be 0.83 bar, which is 12 psi, and 50 meters would equal 4.2 bar, or 61 psi, or 100 meters would be equal to 8.3 bar, which is 120 psi. If we look at some practical real-world examples, a tank of water 20 meters high, the pressure at the tap is equal to 2 bar, which is equal to 200 kPa, which is 29 psi. If you look at an oil storage tank, and the liquid height is 30 meters, the pressure will be 3 bar, or 43 psi. All right, let's have a look at a pressure head unit comparison summary. If we look at pressure, the metric units are bar and kPa. For imperial, that is psi. Liquid head in meters, and imperial will be in feet. Key relation is 10 meters is equal to 1 bar. And for imperial, 2.3, 1 foot is equal to 1 psi. A quick memory card, 1 bar is equal to 100 kPa, which is equal to 14.5 psi. 10 meters of water is equal to 1 bar. 2.31 feet of water is equal to 1 psi. Pressure increases linearly with depth. Definition of pressure in liquid. Liquid has its own weight. This causes pressure on the wall of the container in which liquid is held. It also causes pressure on any object immersed in the liquid. Pressure acts in all directions. Pressure acting on a liquid at rest will be transmitted equally in all directions. This is the end of part number 1. And I hope if you've liked this part of the video so far that you will show that you like it, subscribe to it, share, comment and follow. And thank you for watching.